The universe is whispering to us through tiny ripples in space-time. These gravitational waves carry messages from colossal events that occurred billions of years ago, events we could never hope to see with light alone. By the end of this journey, you will understand how these cosmic messengers are revealing a hidden architecture that governs everything, from the birth of galaxies to the fate of the cosmos itself. We will uncover how the violent dance of black holes and the faint echoes of creation itself are rewriting the rules of reality. What invisible forces are shaping the universe around you right now? Think of the calm surface of a pond the instant after a single pebble drops. That first perfect ripple expands outward, a traveling distortion of the water itself. Gravitational waves are the universe's version of that ripple, but instead of disturbing water, they are literal waves in the fabric of space-time. This was one of the most startling predictions of Albert Einstein's theory of general relativity, made over a century ago. He realized that space is not a static stage, but a dynamic, flexible material. When truly massive objects accelerate, like two black holes whirling around each other in a final, furious dance, they don't just move through space. They shake it. The resulting waves travel outward at the speed of light, not as a substance, but as a rhythmic stretching and squeezing of space itself. As you sit there, a gravitational wave could be passing through you, compressing the space in one direction while expanding it in another, all on a scale so tiny it is utterly imperceptible without the most sensitive machines ever built. Physicist Kip Thorne beautifully calls this the music of the cosmos, a symphony of vibrations that carry a precise story of their violent birth. To understand this music, we listen for its properties, its amplitude, which is its volume, its frequency, which is its pitch, and its polarization, the pattern of how it contorts space. It was this symphony that the LIGO Observatory first heard directly in 2015, a historic chirp from two black holes colliding over 1 billion light-years away. For the first time, we didn't just see the universe, we could listen to it. This single detection opened an entirely new window, allowing us to hear the dark, silent events that light can never reveal. But how do you build an ear sensitive enough to hear a space-time ripple from 1 billion years ago? The answer lies in one of the most ambitious experiments humanity has ever undertaken. These instruments of discovery look nothing like a traditional observatory. Picture two concrete tunnels, each stretching for 2.5 miles, meeting to form a giant L shape laid upon the landscape. Inside these tunnels, a perfect vacuum is maintained, cleaner than the void between planets. Down these immense tubes, powerful laser beams are split and sent racing to the far ends, where they bounce off mirrors suspended with unimaginable precision. In a universe without gravitational waves, the light in each arm would travel the exact same distance, returning to cancel each other out in perfect, silent darkness. But when a ripple from a distant cosmic collision passes through, it does something extraordinary. It subtly stretches the length of one arm while squeezing the other. For just an instant, the laser beams are thrown out of sync, and a flicker of light escapes the darkness. This flicker is the signal. This is the core principle of a laser interferometer, the technology behind observatories like LIGO and Virgo. The challenge and the true marvel is the scale of the measurement. The distortion these instruments are built to detect is almost absurdly small. We are talking about a change in distance thousands of times smaller than the width of a single proton. To sense such a whisper, every conceivable source of noise must be silenced. The mirrors are suspended on complex pendulum systems to isolate them from the constant rumble of earthquakes, passing trucks, and even ocean waves crashing on distant shores. They are shielded in vacuum chambers to prevent the gentle buffeting of air molecules. The laser light itself is manipulated to smooth out the quantum jitter of its own photons. It was physicist Rainer Weiss who, decades ago, first detailed this ambitious design, a vision that required a global collaboration of scientists and engineers working for generations to bring to life. And this is just the beginning of our new sense of hearing. The next generation of detectors will be built in space, free from the terrestrial vibrations that limit our Earth-bound ears. The planned LISA mission will consist of 3 spacecraft, flying in a vast triangle millions of miles apart, using laser links to sense the low-frequency groans of supermassive black holes merging at the hearts of galaxies. Another method uses the universe itself as an instrument. Pulsar timing arrays rely on networks of rapidly spinning neutron stars, which act as cosmic lighthouses emitting beams of radio waves with metronome-like regularity. By monitoring these celestial clocks across our galaxy, astronomers can detect the subtle timing shifts caused by the background hum of gravitational waves from countless collisions over cosmic time. Each of these technological leaps, from earthly lasers to space-based observatories and galactic clocks, is like tuning our ears to a new octave of the cosmic symphony. They allow us to map structures and events that have remained entirely hidden until now. So what are these cosmic events creating the profound signals we strain to hear? 2 black holes locked in a final embrace offer a perfect example of this cosmic violence. Each of these invisible giants carries the mass of dozens of suns, compressed into a region of space smaller than a city. As they orbit one another, their immense gravity churns the spacetime around them, sending out powerful ripples that carry away energy. This loss of energy tightens their spiral, accelerating their dance into a final, furious rush. In the last fraction of a second before they merge, they orbit at nearly the speed of light, and the resulting gravitational wave signal rises to a crescendo, a characteristic chirp that our detectors can now recognize. The collision itself is a storm of unimaginable power, often outshining for a brief moment every star in the observable universe combined. Yet it produces no light, only a ringing in the fabric of space. This is the prime signal that observatories like LIGO are built to catch, a direct message from the darkest objects in existence. But black holes are not the only performers in this symphony. Neutron stars, the ultra-dense corpses of exploded stars, also engage in these fatal dances. A single teaspoon of neutron star material would weigh billions of tons on Earth. When 2 of them collide, the event is even more rich with information. Unlike the silent merger of black holes, a neutron star collision is a multi-messenger event. It often produces a spectacular flash of light across the electromagnetic spectrum, from gamma rays to visible light, and even creates heavy elements like gold and platinum, scattering them into space. The historic detection in 2017 was a landmark moment, as astronomers saw both the gravitational waves and the light from the same cosmic crash, confirming that these collisions are indeed the cosmic forges for the universe's most precious elements. Beyond these dramatic crashes, there are other, more subtle sources. A lone, spinning neutron star with a tiny mountain on its surface, a mere imperfection a few inches high, will create a continuous, faint hum of gravitational waves. A supernova, if its core collapse is lopsided, can send out a powerful, one-off burst. And then there is the most elusive signal of all, the stochastic background, a faint hiss that is the combined rumble of every gravitational wave event throughout cosmic history, a fossil imprint from the Big Bang itself. As expert Alessandro Buonanno has pointed out, Each type of source is like a different instrument in the orchestra, telling us a unique story about the extremes of matter, gravity, and the evolution of the cosmos. So what do these dark messengers reveal about the universe's grand design? The answer lies in the architects themselves, the black holes whose mergers are rewriting our understanding of cosmic structure. A black hole is a region where gravity has won a total victory. It is a puncture in the fabric of spacetime so deep that nothing, not even a beam of light, can climb back out. Yet in their silent darkness, these objects are anything but passive. When two black holes orbit one another, they become the universe's most powerful architects, using gravitational waves as their chisels. Every ripple they send out is encoded with the story of their creation. The precise shape of the wave, its rising chirp and final ring, reveals their masses, how fast they were spinning, and the intricate dynamics of their final dance. This gives us a clean, direct test of Einstein's theory of gravity under the most extreme conditions imaginable. For decades, we thought black holes were simple, defined only by their mass and spin. But as Stephen Hawking and others theorized, they might possess subtle features whimsically called hair, which are tiny distinctions in their gravitational fields. Gravitational waves are our only hope for detecting this hair, for seeing the fine print written on the event horizon itself. The data we are collecting is already reshaping our cosmic family tree. We have confirmed the existence of so-called intermediate mass black holes, objects with thousands of times the mass of our Sun. These are the missing links, the potential seeds that could grow into the supermassive monsters lurking at the center of every galaxy. This is where their role as architects becomes truly profound. When black holes merge, the resulting recoil can kick the new, larger black hole clear out of its host galaxy, sending it wandering into the intergalactic void. More importantly, the energy they release through these mergers and through their voracious feeding influences the formation of stars and the distribution of the mysterious dark matter that binds the cosmos together. It is a form of cosmic feedback, a gravitational pressure that helps sculpt the vast, web-like structure of the universe. So how do we move from observing these individual collisions to understanding the grand tapestry they weave? This cosmic architecture resembles a colossal spider's web, with shimmering strands of galaxies woven around vast, empty voids. Gravitational waves provide our first real tool for mapping the invisible threads of this web. As these ripples travel for billions of years across the cosmos, their journey is not through empty space. They pass through immense clouds of dark matter and skirt the gravitational wells of galaxy clusters. This journey leaves subtle imprints on the waves themselves, a phenomenon akin to a lens bending light. A massive structure between us and the source can act as a gravitational lens, subtly distorting the wave, perhaps creating multiple echo-like copies of the same cosmic event arriving at different times. By analyzing these distortions, we can literally trace the outline of unseen dark matter halos and the faint filaments that connect them, using the waves as our probe. Cosmologist Jana Levin highlights that this gives us a dynamic view of the universe's skeleton, revealing how it grows and evolves over time. For example, when we eventually detect the low-frequency rumble of supermassive black holes merging, their signals will act as tracers, showing us how galaxies themselves have collided and combined throughout cosmic history. This directly tests the theory of hierarchical clustering, the idea that the universe built itself from the bottom up, with small structures merging to assemble the grand galaxies we see today. What role does the mysterious dark matter play in this architectural blueprint? Its gravitational pull provides the essential scaffolding, the framework upon which the entire visible universe is built. Dark matter is the silent partner in the universe's construction project, an invisible substance that provides the essential scaffolding for everything we see. Think of it as the hidden framework of a building, completely concealed behind the walls, yet without its strength, the entire structure would collapse. This mysterious material makes up roughly 27% of the cosmos. It does not emit, absorb, or reflect any light, making it completely transparent to our telescopes. Its only known interaction is through gravity, and its collective pull is what first gathered clouds of primordial gas into the first galaxies, and now holds those vast islands of stars together. We know it is there because we can see its gravitational handiwork, the way it bends the path of light and dictates the motion of stars within galaxies. Yet its fundamental nature remains one of the greatest puzzles in all of science. Gravitational waves offer a unique new way to probe this enigma. While dark matter itself does not create these ripples directly, its pervasive presence leaves a fingerprint on the waves that travel through it. A gravitational wave passing through a dense halo of dark matter will be subtly altered, its path minutely bent and its signal slightly distorted in a process known as weak lensing. By carefully studying these tiny imprints on signals from distant black hole mergers, we can begin to chart the distribution of this invisible substance, mapping its hidden geography across the cosmos. Some theoretical physicists like Paolo Pani are investigating even more exotic possibilities. Could dark matter form unique, compact objects itself? One compelling idea is that a portion of dark matter could be made of primordial black holes, tiny remnants forged in the extreme density of the Big Bang. If these objects exist, their collisions would produce gravitational waves we could detect, revealing a dark matter component we never knew existed. In other scenarios, dense clumps of dark matter particles could annihilate or decay, generating a faint, persistent background hum of gravitational radiation. Even the way binary black holes spiral together could be affected if they are orbiting within a thick cloud of dark matter, their in-spiral rate subtly changing in a way that betrays the presence of the unseen material. Each of these methods turns the gravitational wave into a cosmic messenger, carrying not just news of black holes, but encoded information about the invisible sea of dark matter through which it traveled. This brings us to an even deeper cosmic mystery, one that governs the ultimate fate of the entire universe. If dark matter is the scaffolding that builds cosmic structure, what is the force that is actively tearing it all apart? While dark matter builds the cosmic architecture, a far more mysterious force is actively working to dismantle it. This is dark energy, a repulsive force that permeates all of space, causing the expansion of the universe to accelerate. It is the dominant component of the cosmos, making up about 68% of the universe's total energy. Imagine gravity as the force that pulls the universe together, building galaxies and clusters. Dark energy is its opposite, a cosmic pressure that pushes everything apart on the largest scales. Its discovery in the late 1990s was a profound shock, revealing that the cosmos is not just expanding, but that its expansion is speeding up over time. This acceleration dictates the ultimate fate of the universe, leading to a cold, empty, and ever-dispersing future. But what is this mysterious energy? Is it a constant feature of the vacuum of space, as Einstein once proposed with his cosmological constant? Or is it a dynamic field that changes over the lifetime of the cosmos? Gravitational waves are now providing a revolutionary way to find out. They do this by acting as what astronomers call standard sirens. The name is a perfect description. When two black holes or neutron stars spiral together and merge, the gravitational waves they emit carry a direct, built-in record of their distance. The amplitude of the wave, its loudness, tells us how far away the cataclysm occurred. This is completely independent of the traditional cosmic distance ladder, which relies on a chain of measurements using stars and supernova. By comparing this pure gravitational wave distance with the redshift of the host galaxy observed by telescopes, we get a direct and incredibly clean measurement of the universe's expansion rate, known as the Hubble constant. This method, championed by experts like Daniel Halls, cuts through the astronomical clutter. Currently, there is a troubling tension between different methods of measuring the Hubble constant. Some techniques using the early universe's afterglow suggest one rate of expansion, while methods using nearby supernova suggest a slightly faster one. This discrepancy could be a hint of new physics, a sign that our understanding of dark energy is incomplete. Future observatories are poised to resolve this. The space-based LISA mission will detect merging supermassive black holes, using them as sirens to trace expansion across billions of years of cosmic history. Third-generation ground detectors will hear so many collisions that we can map the expansion rate with stunning precision. This data will allow us to test the nature of dark energy itself. Is it truly a constant, or does its strength wax and wane over time? The answer determines whether the universe will expand forever into infinite emptiness, or if some other, even stranger destiny awaits. To find the origin of this cosmic struggle between dark energy and dark matter, we must journey back to the very beginning to listen for the faintest echoes of creation itself. The faintest hum in the cosmic symphony could carry a message from the very dawn of time. To understand where the universe's grand architecture came from, we must journey back to the first fleeting instance after the Big Bang, to an event known as cosmic inflation. In a span of time so short it defies comprehension, a fraction of a second, the universe is thought to have undergone a breathtaking growth spurt, expanding exponentially and smoothing itself out to an incredible degree. This inflationary period did more than just stretch the cosmos. It took the microscopic quantum jitters, the tiny fluctuations that are a fundamental part of reality, and stretched them to cosmic proportions. These stretched wrinkles in spacetime became the primordial seeds for everything that followed. The denser regions would eventually, over billions of years, collapse under their own gravity to form the vast cosmic web of galaxies and clusters we see today. But inflation left another, even more subtle signature. The violent stretching of spacetime itself should have generated a storm of gravitational waves, ripples that have been traveling through the universe ever since. These waves would have a unique character, creating a stochastic background, a low, steady hiss that underlies all the louder chirps and bursts from black hole mergers. Detecting this primordial background would be like listening to the fossilized echo of creation itself. How could we possibly hear such a faint whisper from the beginning of everything? The hunt is already underway through ingenious methods. One promising avenue is to study the oldest light in the universe, the cosmic microwave background. As this light traveled through the infant cosmos, the gravitational waves from inflation would have left a distinct curling pattern, a specific type of polarization, imprinted upon it. Experiments are actively scanning the sky for this faint fingerprint. Future space-based gravitational wave observatories, designed to sense the lowest frequencies, might one day detect this background directly. As theorist Alan Guth, one of the architects of inflation, has suggested, the properties of these waves would be a direct probe of the energy scales and dynamics of that primordial epoch. They could tell us which of the many proposed models of inflation is correct, revealing physics at energies so high they are forever beyond the reach of any particle collider we could ever build. This background hum is the ultimate fossil, a recording of the universe's first moments, and it was from those initial seeds planted by inflation that the first cosmic structures would eventually begin to form, leading to the birth of the very first stars and galaxies. Out of the primordial darkness came the first cosmic dawn. For hundreds of millions of years after the Big Bang, the universe was a silent, featureless sea of hydrogen and helium gas, shrouded in an impenetrable fog. Then gravity began its patient work, pulling together the densest patches of this pristine gas. Within these collapsing clouds, the very first stars were born. Astronomers call them population 3 stars, and they were unlike anything that exists today. These titans were hundreds of times more massive than our sun, burning ferociously hot and bright, and living lives that were spectacularly brief. Their deaths were just as monumental. After only a few million years, they exploded as cataclysmic supernova, or in the most massive cases, collapsed directly into black holes without any explosion at all. These violent deaths were the universe's first great act of creation and destruction. They seeded the surrounding gas with the first heavy elements, the carbon, oxygen, and iron that would later form planets and life. And they left behind the very first black holes, the seeds from which the cosmic architecture would grow. This entire era, the formation and death of the first stars and the assembly of the first galaxies, is incredibly difficult to observe with traditional telescopes. The light from that time is now incredibly faint, stretched into the infrared by the universe's expansion, and often hidden behind that early cosmic fog. This is where gravitational waves offer a direct line back to that formative age. If those first generation of stars were born in binary pairs, their final dance as black holes or neutron stars would send ripples across spacetime that we could detect today. The specific frequencies and masses recorded in these waves would be a time capsule. They would tell us the size of those first stars, confirming or refuting our models of the initial mass function, which is the distribution of stellar sizes at the dawn of time. As expert Volker Braun has suggested, detecting these waves would also reveal the powerful feedback from those early supernova. The force of those explosions could either trigger new star formation in neighboring gas clouds or blow the gas away entirely, preventing new stars from forming for eons. This feedback mechanism is a critical but poorly understood part of how galaxies regulate their own growth. The gravitational wave background from countless mergers in this early epoch would encode the intensity of this feedback, painting a dynamic picture of how the first structures sculpted their own environments. Furthermore, the faint signals from the mergers of the very first supermassive black hole seeds in the cores of infant galaxies would trace their growth histories, showing us how they started small and grew, through merger after merger, into the behemoths that power quasars. This elusive era, now hidden from our eyes, set the entire stage for the universe we inhabit. Every element in our bodies, every galaxy in the sky, owes its existence to the brief, brilliant lives and violent deaths of those first stars. With this new window into the cosmic dawn, we are not just looking back in time. We are testing the very laws of physics under conditions so extreme they push our theories to the breaking point. The violent embrace of 2 black holes is the ultimate testing ground for the laws of physics. Here, in the strong gravitational field near the event horizon, gravity ceases to be the gentle force that holds our feet to the ground. It becomes a cosmic whirlpool, warping spacetime so severely that the simpler rules of Newtonian physics completely break down. Einstein's theory of general relativity makes very specific and often bizarre predictions for these environments. Gravitational waves provide our cleanest and most direct way to test them. Every ripple that reaches us carries an encoded blueprint of the event that created it, a waveform whose precise shape depends entirely on the underlying theory of gravity. By comparing the observed waves to the predictions of general relativity, we can check for even the tiniest of discrepancies. So far, the theory has passed every test with flying colors. The mergers we have detected confirm that gravitational waves travel at the speed of light, just as Einstein predicted. The final ring down of a newly formed black hole suggests these objects are indeed the simple, bald entities described by the theory, possessing no hair, no complicated surface features. But the search is only beginning. As physicist Clifford Will has highlighted, future observations with more sensitive detectors will push these tests into uncharted territory. What if we find a subtle deviation, a slight anomaly in how the waves are polarized, or evidence that they disperse or spread out as they travel across the cosmos? Such a discovery would be monumental. It could be the first hint of new physics, a sign that gravity behaves differently in these extreme regimes. One tantalizing possibility is the existence of extraspatial dimensions beyond the three we experience. In some theories, gravity could be weaker than expected because it leaks into these hidden dimensions, an effect that would leave a tiny fingerprint on a gravitational wave signal. Another idea is that we are seeing the first echoes of a theory of quantum gravity, a framework that would finally unite the world of the very large, governed by gravity, with the world of the very small, ruled by quantum mechanics. For decades, unifying these two pillars of physics has been the single greatest challenge in theoretical physics. Gravitational waves are now providing real, observational data from the one place where both theories must meet, the edge of a black hole. This quest to understand gravity in its purest form inevitably leads us to a broader picture. How do these ripples in spacetime interact with the other fundamental forces of nature? The answer lies in watching cosmic events unfold through every possible messenger. A single cosmic event can now tell its story through multiple voices. This is the power of multi-messenger astronomy, a revolutionary approach that combines different cosmic signals to build a complete picture. Before this era, astronomers were like people trying to understand a complex movie by watching only a single frame. They could see the light, but they were missing the sound, the plot, and the emotional depth. Now, by listening for gravitational waves while simultaneously watching with telescopes for light across all wavelengths, from radio waves to gamma rays, and even detecting elusive particles called neutrinos, we are experiencing the universe in its full, multidimensional glory. The landmark event known as GW 170817 was our first true taste of this new reality. In August of 2017, gravitational wave observatories detected the telltale chirp of two neutron stars colliding. Within seconds, telescopes around the world and in space were alerted, swiveling to the same patch of sky. What they witnessed was a kilonova, a spectacular explosion of light that confirmed these violent mergers are the cosmic forges where heavy elements like gold, platinum, and uranium are created. The gold in your wedding ring was likely born in such a cataclysmic event billions of years ago. This single observation did more than just solve a long-standing mystery. By having both a gravitational wave distance and an optical measurement of the host galaxy's redshift, it provided one of the most direct and independent measurements of the universe's expansion rate, sharpening our view of dark energy. As David Rietzi of LIGO has emphasized, this success was only possible through a seamless, global collaboration. When a gravitational wave signal arrives, automated alerts are sent to hundreds of observatories worldwide, creating a coordinated, planet-sized instrument poised to capture every facet of a cosmic drama. This coordinated effort is crucial for probing the most extreme environments. For decades, the origin of short gamma-ray bursts, the most powerful explosion since the Big Bang, was a subject of intense debate. Multi-messenger observations have now definitively linked them to neutron star mergers, revealing the physics of the relativistic jets they produce. By seeing the event in gravitational waves and light, we understand the engine, the fuel, and the aftermath all at once. This holistic view is transforming our understanding of cosmic phenomena from isolated curiosities into interconnected chapters of a single physical story. The technological advances driving this revolution are pushing the very limits of our ingenuity. The next generation of gravitational wave observatories will transform our cosmic hearing from a faint whisper into a resounding chorus. Here on Earth, ambitious projects are moving from blueprint to reality. The Einstein telescope planned deep underground in Europe and Cosmic Explorer, a proposed larger version of LIGO in the United States, are not mere upgrades. They represent a quantum leap. By increasing sensitivity by an order of magnitude, these third-generation detectors will peer 10 times further into the cosmos. This means surveying a volume of space 1,000 times larger than our current view. We will no longer just hear the loudest, closest black hole collisions. We will detect the faint, distant chirps from the universe's first stellar black holes, witnessing the assembly of cosmic structure across time. They will capture the gravitational waves from neutron star mergers with such exquisite detail that we can study the exotic state of matter at their cores, a substance denser than an atomic nucleus. Every ripple will be measured with a new level of precision, revealing subtle details in the waveform that could finally reveal the hair, the unique fingerprints of individual black holes. But to hear the deepest notes of the cosmic symphony, we must escape the terrestrial noise entirely. The Laser Interferometer Space Antenna, or LISA, is a mission that will do just that. Scheduled for launch in the 2030s, LISA will consist of 3 spacecraft, flying in a perfect triangle millions of miles apart, connected by laser beams. Free from the constant rumbling of Earth, this space-based observatory will be tuned to the low-frequency gravitational waves that are completely inaccessible from the ground. It will listen for the stately, million-year dance of supermassive black hole binaries as they orbit at the hearts of distant galaxies. We will hear their slow in-spiral long before they finally collide. LISA will also detect the cacophony of hundreds of thousands of binary white dwarf stars within our own Milky Way, a steady gravitational hum from our celestial backyard. As lead scientist Carsten Dansman often explains, this will allow us to chart the population of these stellar remnants and map the gravitational landscape of our galaxy in an entirely new way. Beyond LISA, even more advanced concepts are on the drawing board. The DeSigo mission aims to probe the intermediate frequency band, potentially detecting the primordial waves from inflation directly. And a new technology using atomic interferometry could one day use clouds of ultra-cold atoms as incredibly precise sensors of spacetime distortions. Together, this coming fleet of observatories will create a full-spectrum gravitational ear. We will track the growth of black holes from the earliest times to the present, witness the entire history of galactic collisions, and potentially hear the birth cry of the universe itself. This impending flood of data does more than just add to our knowledge. It forces us to confront profound questions about our place in the cosmos. This quiet tension in cosmology points to a fundamental question: how fast is our universe really expanding? Different methods for measuring this rate, known as the Hubble constant, have begun to yield stubbornly inconsistent answers. It is a discrepancy that has left cosmologists perplexed. One set of measurements based on the ancient afterglow of the Big Bang suggests one speed. Another, using supernova in the relatively recent universe, suggests a slightly faster one. The gap between them is small, but it refuses to close, hinting that our standard model of cosmology might be missing a crucial piece. This is where the pure tone of a gravitational wave becomes a decisive instrument. When two black holes or neutron stars merge, the gravitational waves they emit act as what astronomers call standard sirens. The beauty of this method is its directness. The loudness of the wave, its amplitude, gives us a direct measure of the distance to the collision, completely independent of the traditional cosmic distance ladder with all its potential for accumulated error. By then finding the host galaxy with a telescope and measuring its redshift, how much its light has been stretched by the expansion of space, we get a clean, powerful way to calculate the Hubble constant. Early observations from the LIGO and Virgo collaborations have already begun to weigh in on this debate. While individual events provide valuable data points, it is the growing collection of them that is progressively narrowing the range of possible values. As cosmologist Wendy Friedman and others have noted, gravitational waves are emerging as a key tool for precision cosmology. If the tension in the Hubble constant persists even with this pristine new data, it would be a strong indicator that new physics is at play, perhaps a subtle evolution in the nature of dark energy itself. Resolving this puzzle is not just an academic exercise. The expansion rate is a foundational parameter. It determines the universe's age, its size, and its ultimate fate. Pinpointing it with certainty would be a monumental milestone, anchoring our cosmic timeline and clarifying the long-term destiny of everything we see. Yet beneath the individual chirps of these standard sirens lies a far more subtle sound, a constant murmur from the combined rumble of every cosmic collision throughout time. Beneath the distinct chirps of individual black hole collisions lies a far more subtle sound, a collective murmur from the entire history of the cosmos. This is the stochastic gravitational wave background, a faint, persistent hum created by the superposition of countless unresolved sources. It is not a single event, but a statistical whisper, the combined rumble of every binary merger, every cosmic catastrophe that has ever occurred, all layered on top of one another into a steady hiss. This background could have two primary origins. The first is astrophysical, the cacophony of millions upon millions of binary black holes and neutron stars throughout cosmic history, their individual signals too faint and numerous to distinguish, blending together into a continuous ocean of vibration. The second origin is far more profound and cosmological. This hum could contain the fossilized ripples from the universe's earliest moments, generated by processes like cosmic inflation or violent phase transitions. Think of it as the gravitational equivalent of the cosmic microwave background. While that ancient light shows us a picture of the infant universe, this gravitational wave hum would let us hear its very first vibrations, the primal tremors of creation itself. Researchers like Joseph Romano are at the forefront of developing the sophisticated data analysis techniques needed to extract this incredibly faint signal from the dominant noise. One of the most promising methods uses the universe itself as a detector. Pulsar timing arrays monitor networks of these spinning neutron stars, which act as celestial metronomes. A passing stochastic background would minutely alter the arrival times of their pulses across the entire galaxy, creating a correlated pattern that sophisticated algorithms can uncover. A confirmed detection would be a monumental achievement, offering a statistical view into the universe's most violent eras and potentially revealing new high-energy physics. It forces us to ask what kind of dramatic phase transitions could have shaken the fabric of spacetime so profoundly in its first instance. The newborn universe was a seething cauldron of pure energy, cooling with unimaginable speed. As it expanded and its temperature plummeted, it underwent profound shifts, much like steam condensing into water or water freezing into ice. These cosmic phase transitions were not mere changes of state. They were moments when the fundamental symmetries of reality itself were broken, releasing colossal amounts of latent energy into the fabric of spacetime. In the most dramatic scenario, known as a first-order phase transition, this change did not happen smoothly everywhere at once. Instead, bubbles of a new, more stable vacuum would spontaneously form and rapidly expand at nearly the speed of light. Think of a pot of superheated water suddenly erupting into bubbles of steam. In the primordial cosmos, these colliding vacuum bubbles would have created violent ripples in spacetime, a chaotic storm of gravitational waves that would persist to this day as a distinctive hum in the stochastic background. This is not just a theoretical curiosity. The specific frequency and amplitude of this hum are a direct recording of the energy scales at which these transitions occurred. If we can detect it, we will be reading the energy signature of the universe's infancy. This is why experts like Chiara Caprini point to future space-based observatories like LISA as our best hope. These instruments will be tuned to the low frequency range where the rumble from these primordial bubbles would be found. A detection would be more than just a confirmation of a hot, early universe. It would be a direct probe of physics at energy scales of tera-electron volts and beyond, realms forever out of reach for even the most powerful particle colliders on Earth. Such a discovery could illuminate the path to theories that unite the fundamental forces, ideas like grand unification or supersymmetry. It might even explain one of the universe's greatest imbalances, baryogenesis, the process that created slightly more matter than antimatter, allowing everything we see to exist. It could also reveal how dark matter itself was forged in those first fiery moments. These gravitational waves are therefore a fossil record of the universe's thermal history, a timeline of its cooling and the dramatic rearrangements of the laws of physics that occurred along the way. This profound connection forces us to ask an even deeper question. If these ripples can tell us about the universe's first moments, what do they reveal about the very nature of the stage upon which everything plays out? This dynamic nature of spacetime means its very geometry is written into the waves we detect. Each ripple is not just a messenger from a distant collision. It is a direct sample of the fabric of the cosmos, stretched and squeezed by the event that created it. This allows us to ask an almost philosophical question. Is spacetime a perfectly smooth and continuous sheet, as Einstein's theory presumes, or does it have a grainy, discrete structure when viewed at the smallest possible scales? At the unimaginably tiny Planck scale, a distance of 10 to the negative 35 meters, the universe might be a seething foam of virtual wormholes and quantum fluctuations. This is the realm where gravity and quantum mechanics must finally meet, and gravitational waves are our only conceivable probe. Some of the most ambitious theories in physics, like loop quantum gravity and string theory, predict that this fundamental graininess would leave a subtle imprint. As a gravitational wave travels across billions of light years, its journey through this quantum foam could slightly alter its properties. It might scatter, or its polarization could shift in a way that betrays the hidden texture of reality. Future observatories, with their immense sensitivity, will search for these tiny deviations. They will look for faint echoes following the main ring of a black hole merger, a potential sign of quantum structure just outside the event horizon. As physicist Carlo Rovelli suggests, finding such an echo would be like hearing the individual atoms of spacetime itself. It could provide the first experimental evidence for the existence of the graviton, the hypothetical quantum particle that carries the gravitational force. This search transforms an abstract philosophical puzzle into a tangible, observational science. The very waves that reveal the architecture of the cosmos could also reveal the fundamental substance from which that architecture is built. These profound implications for the nature of reality inevitably lead our curiosity outward. If gravity and spacetime have a quantum structure, and if life can emerge in such a universe, could other intelligences be using this same cosmic medium to communicate? The very fabric of spacetime might carry more than just the echoes of cosmic collisions. What if it also carried messages? This is the speculative frontier where gravitational wave astronomy intersects with the search for extraterrestrial intelligence. Some theorists, like Claudio Maccone, propose that an advanced civilization, operating on a scale we can barely conceive, might use gravitational waves for communication. The reasoning is compelling. Unlike radio waves, which scatter and weaken over interstellar distances, gravitational waves travel almost unimpeded through cosmic dust and gas. A deliberate, engineered signal pulsed into the fabric of spacetime could cross the galaxy with stunning clarity, a whisper in the cosmic static that endures for eons. Finding such a signal would be the ultimate discovery, but it is a monumental challenge. It would require sifting through the chaotic data of black hole mergers and neutron star crashes, looking for patterns that defy natural explanation, a sequence too perfect, too structured, to be born from random violence. This search demands new forms of artificial intelligence and pattern recognition, algorithms trained to spot the signature of intelligence within the noise of nature. Beyond communication, we can speculate about even grander works. Could a truly advanced species build on a cosmic scale? Imagine a Dyson sphere, a vast structure enveloping a star to harness its entire energy output. If such a megastructure were to collapse or be deliberately moved, the immense shift of mass could generate a unique, low-frequency gravitational wave pulse. Or consider a civilization that learned to feed a star into a black hole, creating a controlled engine of unimaginable power. The specific, steady frequency of gravitational waves from such a managed system would stand out against the random bursts of the natural cosmos. While these ideas remain firmly in the realm of speculation, they expand the canvas of SETI from the electromagnetic spectrum to the gravitational, asking us to listen for not just what is said, but for the shudder of colossal industry. This leads to a more immediate question for our own future. How might humanity itself one day use this hidden architecture? The answer could redefine our path to the stars. Practical applications for space travel are already being seriously studied. One of the greatest challenges of interstellar travel is propulsion. Conventional rockets are hopelessly slow for crossing the vast gulfs between stars. But what if we could ride the very ripples of space-time? While we lack the technology to generate significant gravitational waves ourselves, understanding them could lead to a deeper mastery of gravity. If we can one day comprehend gravity not just as a force, but as a malleable field to be shaped, it might open the door to concepts like warp drives or gravity control. Such technologies would not involve creating massive waves, but rather subtly manipulating the space-time metric around a spacecraft, effectively allowing it to surf on the fabric of the cosmos. Furthermore, by mapping the gravitational wave background of our galaxy, future navigators could use these ripples as a cosmic lighthouse system. Just as sailors once used stars, a starship could triangulate its position by locking onto the steady hum of binary white dwarfs or the distant chirp of merging black holes, creating a gravitational GPS for the void. This is not science fiction, but a logical extension of our current exploration. Every ripple we detect, every waveform we decode, adds another piece to the puzzle of gravity itself. And with that understanding, we move closer to the day when humanity might not just listen to the music of the cosmos, but learn to play a few notes of its own. The same technology that listens for ripples in spacetime is quietly reshaping our world on a human scale. Consider the laser systems at the heart of LIGO. To detect a shift smaller than a proton, these lasers must be phenomenally stable, their light waves perfectly coherent. This relentless drive for precision has forced breakthroughs in laser design that now benefit other fields. In medicine, improved laser stability is leading to more accurate surgical tools and advanced eye surgery techniques, where a microscopic steady hand is everything. The challenge of isolating those suspended mirrors from the world's constant vibrations has birthed revolutionary vibration damping systems. These sophisticated isolation platforms are now being adapted to protect sensitive electron microscopes in laboratories and to stabilize high-precision manufacturing equipment, ensuring the flawless production of everything from computer chips to medical devices. Even the monumental task of processing the data, of finding that one cosmic chirp in a sea of terrestrial noise, has pushed computer science forward. The advanced algorithms developed to sift through LIGO data are now being applied to improve medical imaging, helping to filter out background fuzz in MRI scans to reveal clearer, more detailed pictures of the human body, aiding in earlier and more accurate diagnosis. This technological cross-pollination extends to our understanding of the planet itself. The field of geodesy, which measures Earth's shape and gravitational field, uses laser ranging techniques that have been refined by the demands of gravitational wave science. These methods provide critical data for tracking sea level rise, monitoring groundwater reserves, and understanding the slow rebound of land masses after the last ice age. As David Shoemaker of LIGO often notes, no one initially set out to build a better medical scanner or a more precise map of Earth's aquifers. These were unplanned dividends emerging from a single-minded pursuit of a fundamental question. This cascade of innovation demonstrates a profound truth about curiosity-driven research. Investing in the seemingly abstract quest to understand black holes does not just fill textbooks. It builds a foundation of new knowledge and new tools that inevitably spill over, solving practical problems and creating new industries in ways that are impossible to predict at the outset. Yet with every new power to perceive and manipulate our world, a new responsibility emerges: the ability to sense the faintest vibrations or to manipulate quantum states raises essential questions. Who controls this sensitive technology, and how do we ensure it is used for the benefit of all? As we peer deeper into the cosmos, we are also forced to look inward, to consider our place and our purpose within this vast, whispering architecture. A gravitational wave is a cosmic reminder that we are not separate observers of the universe, but deeply embedded within its fabric. Every ripple that passes through Earth from a billion-year-old collision is a physical connection to that distant event, a whisper that ties our local patch of spacetime to the most violent processes imaginable. Philosopher Tim Maudlin uses this to make a startling point. The reality of gravitational waves confirms that spacetime is not a passive stage. It is a dynamic, physical thing that can be stretched, squeezed, and set ringing. The void is not empty, it is a vibrant medium, and we are all immersed in it. This cosmic perspective can be profoundly humbling. Our daily worries and conflicts unfold on a scale that is utterly dwarfed by these immense, silent events. Yet, the same physics that governs the dance of black holes also dictates the fall of an apple. We are made of stardust forged in explosions sensed by these very waves, and we are now building the instruments to hear them. This shared cosmic origin and this shared capacity for wonder can foster a powerful sense of unity, a recognition that all of humanity is aboard a single, fragile world, listening together to the music of the cosmos. This awe is not an end in itself. It is the very engine of our curiosity, the driving force behind our relentless quest for meaning and understanding. But how do we translate the complex mathematics of a waveform or the abstract reality of a four-dimensional fabric into a story that resonates with every human heart? The challenge of sharing these profound discoveries brings us to the vital art and science of communication. A gravitational wave signal is a complex mathematical fingerprint, a detailed curve that tells a story of mass, spin, and velocity. Our task is to translate that curve into a narrative anyone can feel. Scientists like Brian Greene have mastered this art, replacing intimidating equations with relatable analogies. He might describe the fabric of spacetime as a vast, invisible trampoline, where massive objects like stars create deep wells and gravitational waves are the ripples that race across its surface. These are not simplifications, but bridges connecting abstract theory to our everyday experience of waves on water or the strum of a guitar string. Science museums take this further, building physical exhibits where you can turn a crank to spin two model black holes and watch a light blink in rhythm with the simulated gravitational waves you are creating. That direct, hands-on interaction transforms a distant concept into a personal discovery. The goal is not to make everyone a physicist, but to ignite that spark of wonder, the same feeling that drives the researchers themselves. This communication effort extends far beyond lecture halls and museum walls. Social media platforms and documentaries have become powerful amplifiers, carrying these cosmic stories directly into our homes. A single animation of colliding black holes shared by a space agency can be seen by millions in a day. These visuals create a shared moment of awe, a collective reminder that humanity is achieving something extraordinary. They inspire a child to look up at the night sky with new questions, or a student to pursue a career in engineering, knowing their skills could one day help build a machine that hears the universe. This broad engagement is vital for more than just funding. It cultivates a society that values evidence, understands the scientific process, and can think critically about the world. When the public grasps the significance of a gravitational wave detection, they are not just learning a fact, they are participating in a fundamental human endeavor, the pursuit of understanding our place in the cosmos. This entire enterprise, from detection to communication, is inherently global. The LIGO observatories are in the United States, but they work in lockstep with the Virgo detector in Italy and the Kagra Observatory in Japan. When a signal arrives, scientists from dozens of countries analyze the data together. This international collaboration is not a formality, it is a necessity. A single detector cannot pinpoint a source in the sky, but three, spread across the globe, can triangulate its location with precision, allowing telescopes worldwide to swing into action. This model of cooperation, where nations contribute resources and expertise toward a common goal, stands as a powerful testament to what humanity can achieve when we look beyond borders. The shared language of science and discovery builds connections that transcend politics, creating a community united by curiosity. The next great discovery will not belong to one nation, but to all of us. This global chorus of discovery relies on a foundation of unprecedented cooperation. When a gravitational wave signal ripples through the detectors, an alert flashes across a network that spans the planet, triggering a coordinated response from telescopes on every continent and in space. This is the work of the LIGO scientific collaboration and the Virgo collaboration, a collective of thousands of scientists, engineers, and students from dozens of countries. They are not competing, they are building a single, distributed instrument of human intellect. From the damp forests of Washington and Louisiana to the Italian countryside near Pisa, these teams pool their data, their brainpower, and their resources. A theorist in Germany might work through the night to model a signal, while a data analyst in India refines the algorithms to pinpoint its origin, and an engineer in Japan ensures the delicate mirrors remain perfectly still. This model accelerates progress exponentially. The historic neutron star merger in 2017 was not just a scientific breakthrough, it was a logistical marvel. Within moments of the gravitational wave detection, astronomers worldwide were pinpointing the flash of light, a rapid-fire global effort that confirmed the origin of heavy elements. As former National Science Foundation Director Franz Cordova has noted, these partnerships are not a luxury, they are a necessity. The grand challenges of modern science, from detecting the faintest cosmic whispers to understanding dark energy, are simply too vast for any one nation to tackle alone. This scientific diplomacy builds bridges that extend far beyond the laboratory. When researchers from different cultures and backgrounds work toward a common goal, they foster a unique form of trust and mutual respect. They share not only data but also perspectives, creating a culture of shared purpose that sets a powerful precedent for cooperation in other global endeavors, from climate science to public health. But perhaps the most enduring legacy of this collaboration is its investment in the future. How do these massive projects contribute to education and the next generation of scientists? They function as a global university. Students and early career researchers are embedded in these international teams from the start. They learn to operate some of the most complex machinery ever built, to write sophisticated software, and to collaborate across time zones and languages. They are not just studying science, they are doing it at the very forefront of human knowledge, contributing to discoveries that make headlines around the world. This hands-on experience creates a diverse, skilled, and globally minded workforce, equipped not only with technical expertise but with the collaborative spirit needed to solve the great puzzles that still lie ahead. This global classroom is already in session, bringing the cosmos directly to students of all ages. In schools around the world, young learners are building simple interferometer models with laser pointers and mirrors, physically grasping the principles that underpin billion-dollar observatories. They are not just memorizing facts, they are recreating the essence of the experiment, feeling the thrill of seeing a laser spot wobble with a gentle tap on the table, a tangible echo of a distant black hole collision. This hands-on approach demystifies complex science, transforming it from an abstract concept into a solvable puzzle. Beyond the classroom, citizen science projects like Einstein at Home harness the collective power of the public. Anyone with a computer can volunteer their spare processing power, their machine becoming a small part of a global network that sifts through real gravitational wave data. These volunteers have co-authored scientific papers, their contributions directly leading to the discovery of previously unknown cosmic events. It is a powerful democratization of discovery, where a teacher in Brazil or a retiree in Japan can actively participate in frontier research. Major scientific organizations amplify this reach. The American Physical Society and NASA provide a wealth of free resources, from interactive online simulations that let you choreograph your own black hole merger to lesson plans that explore the physics of spacetime. These tools break down barriers, making cutting-edge science accessible to every curious mind, regardless of their background or location. At the university level, this inspiration crystallizes into career paths. Institutions are now developing specialized courses in gravitational wave astronomy, a field that did not even exist as a dedicated discipline a generation ago. Undergraduate and graduate students are not just reading textbooks, they are gaining direct research experience, writing code to analyze signals, and working alongside senior scientists on published papers. This direct mentorship is cultivating the next generation of innovators, the future leads for projects like the Einstein telescope and LISA. This intentional investment in education does more than fill jobs. It builds a sustained pipeline of talent and fresh ideas. By actively promoting diversity and inclusion, these programs ensure that the community of scientists exploring the cosmos reflects the diversity of humanity itself. When people from different backgrounds, cultures, and experiences bring their unique perspectives to a problem, they ask different questions and devise novel solutions. This enrichment of the scientific community with varied viewpoints is not just an ethical imperative, it is a practical one, essential for tackling the universe's deepest mysteries. The resonance of these cosmic ripples, however, extends far beyond the laboratory and the lecture hall. The same data that fuels scientific discovery is also inspiring a new wave of artistic expression, translating the music of the cosmos into forms that speak directly to the human soul. The raw data of a gravitational wave is a mathematical curve, a precise but silent story. Artists hear the music within that silence. Composers have taken the actual signals from colliding black holes, the recorded chirps and ring-downs, and transposed them into the range of human hearing, creating symphonies born directly from cosmic violence. You can listen to the death spiral of two neutron stars, its pitch rising in a frantic crescendo that culminates in a single, thunderous chord. This is not an artistic interpretation, it is a direct translation, turning the mathematics of relativity into an emotional experience that resonates in your very bones. Visual artists perform a similar magic with light and form. They take the intricate data from supercomputer simulations, the warping grids of spacetime around merging black holes, and render them into swirling, hypnotic visualizations. These are not just illustrations, they are maps of a reality we can never see with our own eyes, giving form to the invisible architecture of the cosmos. These collaborations are formalized in initiatives like the LIGO Art Science program, which invites painters, musicians, and sculptors to immerse themselves in the science. The goal is not to decorate the research, but to engage with it as a new kind of landscape, a source of profound metaphor and beauty. A painter might spend weeks with astrophysicists, learning the language of wave polarization, then create a canvas where vibrant colors clash and swirl in patterns that feel both chaotic and deeply ordered, mirroring the disturbance in the fabric of reality. This fusion of disciplines reveals a fundamental truth that the drive to understand and the drive to create are two expressions of the same human impulse. We use science to comprehend the universe, and we use art to comprehend our place within it. When a composer turns a billion-year-old spacetime ripple into a string quartet, or a data visualization becomes a stunning light installation in a public square, it does more than just communicate science. It embeds these cosmic discoveries into our shared culture, transforming them from distant headlines into part of our collective story. They remind us that the universe is not just a set of equations, but a source of awe and wonder that has inspired humanity for millennia. How does this cultural absorption of scientific discovery shape what we, as a society, value and prioritize? When the beauty of a gravitational wave is rendered as a sculpture or a song, it argues for the intrinsic worth of curiosity itself. It makes the case for funding fundamental research not just for its practical spin-offs, but for its capacity to enrich the human spirit. This public engagement, fueled by art, builds a broader appreciation for the scientific endeavor, fostering a culture that supports long-term exploration. Yet, the power to sense the faintest cosmic whispers and to shape matter at the quantum level also carries a profound weight of responsibility. This immense power to listen to the cosmos carries with it a deep ethical weight. The very act of building these colossal observatories, which consume significant energy and resources, demands we consider their environmental footprint. Scientists are increasingly tasked with minimizing this impact, exploring green energy solutions and sustainable designs for future detectors, ensuring our quest to understand the universe does not come at an undue cost to our own planet. Beyond the physical footprint lies the responsibility of how knowledge is shared. The global nature of this research hinges on a commitment to open data, where signals are made available to scientists everywhere, fostering transparency and accelerating discovery. Yet this openness must be carefully balanced with fair credit and intellectual property, ensuring that the contributions of all collaborators from every nation are recognized and valued. This is not merely a logistical concern, but a foundational principle for equitable science. Ethicists like Heather Douglas emphasize that such monumental research cannot exist in an ivory tower. It requires an inclusive dialogue, engaging not just scientists, but also policymakers, community leaders, and the public. What are the potential societal impacts of this knowledge? Could a deep understanding of spacetime one day lead to technologies with profound consequences, perhaps even gravitational manipulation? While such applications remain distant, the conversation must begin now, involving diverse voices to guide innovation responsibly. This ongoing dialogue is essential for maintaining public trust. When society invests in these grand projects, it does so with the faith that the pursuit is for the collective good. Balancing the pure, curiosity-driven quest to hear the universe's first whisper with the need to demonstrate tangible benefits is a delicate act. It is a reminder that science is a deeply human endeavor, and its greatest achievements are those that align with our shared values and aspirations for a better future. How might these ripples in spacetime and our growing ability to interpret them ultimately reshape humanity's destiny among the stars? The faint hum of a gravitational wave could one day become the bedrock of our civilization. Envision a network of satellites not merely bouncing radio signals, but using calibrated ripples in spacetime itself to communicate. This is not science fiction, but a logical extension of our growing mastery. The same principles that let us listen to black holes could enable a form of communication that is virtually lossless and secure, traveling directly through planets and stars without distortion. Such a gravitational internet would revolutionize our connection to deep space probes and future colonies, creating an unjammable cosmic web. Navigation would be transformed, with spacecraft triangulating their position using the steady, predictable chirps from known binary pulsars as celestial lighthouses, a gravitational GPS guiding humanity safely through the interstellar void. The energy locked within spacetime's vibrations is another tantalizing frontier. While we cannot yet harness it, understanding how massive objects lose energy to gravitational waves brings us closer to the fundamental relationship between mass, energy, and the fabric of the cosmos. This knowledge might one day unlock new principles of energy generation, or lead to propulsion systems that manipulate gravity itself, allowing ships to surf on the geometry of space rather than pushing against it with rockets. These staggering possibilities all spring from a single source: our investment in fundamental, curiosity-driven research. The laser stabilizers and vibration isolation systems developed for LIGO were not built with a smartphone in mind, yet they advanced precision engineering for everyone. The quest to understand a black hole merger forces us to push the boundaries of quantum computing and materials science, creating tools that will inevitably find applications we cannot yet conceive. This pipeline from pure question to practical revolution underscores a vital truth. that our future technological prowess is being written today in the data streams of gravitational observatories. But such transformative potential cannot be the project of a single nation. The challenges of building a space-based interferometer or a next-generation terrestrial detector demand a global consortium sharing costs, risks, and intellect. This cooperative model does more than accelerate discovery. It builds the diplomatic and logistical frameworks necessary for humanity to act as a unified species when facing other grand challenges, from climate change to asteroid deflection. A crucial question then emerges from this collaborative future. How do we ensure that the benefits of such cosmic technologies, from flawless navigation to profound new energy sources, are distributed fairly across the world? The answer lies not only in the laboratories, but in the halls of government and the forums of international policy. Sustained public funding for basic science is the essential seed corn for this future. It requires a long-term vision from policymakers who understand that the greatest returns often come from the most abstract inquiries. We must champion policies that protect open data and foster international partnerships, ensuring that the architecture of our future is built on a foundation of shared knowledge and equitable access for all. The silent symphony of the cosmos relies on a chorus of support from the societies that listen for it. Behind every cosmic chirp detected by LIGO and every future hum to be measured by LISA lies a complex human infrastructure of policy and funding. These monumental projects are not born in a vacuum. They are sustained by decades of strategic investment from government agencies like the National Science Foundation in the United States and the European Space Agency abroad, alongside crucial contributions from private foundations. This funding is the lifeblood of discovery, enabling the long-term planning and technological innovation that these endeavors demand. Securing it requires relentless advocacy from scientific communities, who must continually demonstrate the value of this fundamental research to policymakers and the public. It is a conversation that translates the abstract beauty of spacetime ripples into tangible benefits for society. Leaders like Marcia McNutt, a geophysicist and former president of the National Academy of Sciences, have long argued that strategic investments in fundamental science yield exceptionally high returns. These are not merely expenditures, they are seeds planted in the soil of human knowledge that grow into unforeseen technological forests. The precise lasers developed for gravitational wave detection now refine medical imaging, while the advanced data analysis techniques are applied to climate modeling and financial markets. This cascading innovation is a powerful metric of success, but it is not the only one. How do we truly measure the return on investing in the cosmos? The first milestone is pure discovery itself. The direct detection of gravitational waves in 2015 was a triumph that validated a century-old prediction and opened an entirely new sense for humanity. It was the culmination of a 50-year journey from theoretical concept to operational observatory, a venture that required faith and foresight from funding bodies. Another critical measure is the cultivation of a global, skilled workforce. These projects train generations of engineers, data scientists, and theorists, equipping them with problem-solving skills that permeate every sector of the economy. A third milestone is the strengthening of international partnerships. The LIGO-Virgo-Cagra collaboration is a living testament to what nations can achieve together, building trust and shared purpose that extends far beyond the laboratory. Finally, there is the immeasurable return of inspiration, the cultural shift that occurs when a society collectively turns its ear to the universe and dares to ask profound questions. These milestones together paint a picture of an investment that enriches not just our understanding of physics, but the very fabric of our global society. That single chirp in 2015 was not an ending, but a beginning. It was the moment our species truly learned to listen to the universe, confirming a prediction Einstein made a century prior. Since that historic detection, the whispers have become a steady stream of cosmic conversation. Each new signal is a unique voice in the chorus. The deep thuds of black holes merging tell us about the silent, dark population of stellar corpses drifting through the cosmos. The brighter, richer crashes of neutron stars speak of the violent forges where gold and platinum are born. Every single one of these events provides a crucial test for Einstein's theory of general relativity, and so far, it has passed every one with astonishing precision. This cascade of discovery was a monumental validation not just of a theory, but of human ingenuity. It proved that the impossibly sensitive technology of laser interferometry could indeed capture a vibration smaller than a proton, a feat many thought impossible. The global scientific community recognized this triumph with the 2017 Nobel Prize in Physics, awarded to the founders of LIGO. That award was a tribute to the decades of perseverance and the power of international collaboration, a testament to what we can achieve when we work together toward a seemingly impossible goal. These milestones are more than just entries in a history book. They are the foundation upon which we are building our future understanding of the cosmos. They prove that with patience and shared purpose, we can unlock the universe's deepest secrets, yet for every question answered, a dozen more emerge from the darkness. What is the true nature of the gravitational wave background hum? Can we finally detect the faint ripples from the Big Bang itself? The journey of listening has only just begun. The grand symphony of cosmic collisions has only just begun to play, and already it presents us with profound mysteries. We have heard the loudest chirps, but the faintest hum, the stochastic background, still eludes our ears. Why is this collective whisper from every black hole merger and neutron star crash throughout cosmic history so difficult to detect? The challenge lies in its subtlety. It is not a single event, but a statistical ocean of noise, a hiss that requires years of data and the correlation of signals from dozens of pulsars across the galaxy to even hint at its presence. Finding it would be like trying to hear the roar of a distant stadium crowd over the sound of individual conversations happening right next to you. Researchers like Dr. Maura McLaughlin, who leads pulsar timing array efforts, pour over decades of timing data, searching for that correlated pattern that would confirm we are bathing in this cosmic sea of vibration. Beyond this astrophysical background lies an even more tantalizing prize, the primordial rumble from the universe's birth. What can these waves from the earliest moments tell us about inflation? If we could detect the gravitational waves generated in that first fraction of a second, it would be a direct probe of physics at energies 1 trillion times greater than any particle collider can reach. The properties of that signal would reveal which version of inflation is correct, telling us not just that the universe expanded, but exactly how that explosive growth unfolded. Another towering puzzle concerns the giants at the center of galaxies. How do supermassive black holes weighing millions or even billions of suns form and evolve? Do they start as the remnants of the first stars and grow through countless mergers, or are they born large from the direct collapse of immense gas clouds in the early universe? The future LISA mission is designed to answer this by listening for the low-frequency groans of these monsters as they pair up and spiral together, tracing their growth history across cosmic time. Each of these unanswered questions drives a global community of scientists. In laboratories and universities worldwide, theorists like Dr. Franz Pretorius run immense supercomputer simulations, modeling the complex dance of spacetime around colliding black holes to create templates that data analysts can match against the real signals. Meanwhile, instrumentalists like Dr. Lisa Barsotti work on refining the lasers and mirrors of future detectors, pushing the technology to new levels of quiet and stability. Their collective, painstaking work, from writing lines of code to polishing flawless glass, is all aimed at turning these cosmic mysteries into solvable problems. This ongoing quest is not a solitary one, but a collaborative human effort to listen more closely to the universe, hoping that in its next whisper, we will find the clue that revolutionizes everything we know. The first time she saw a signal appear on her screen, the universe suddenly felt small. She was a graduate student, working a late shift monitoring the LIGO data stream, when a distinct chirp emerged from the usual background noise. In that moment, the abstract equations and years of meticulous preparation crystallized into a tangible event, a cosmic handshake from 1 billion light-years away. She recalls the immediate surge of adrenaline, followed by a profound sense of connection to a cataclysm she would never see, but had now uniquely heard. This personal story, repeated in different forms across the collaboration, is the human heartbeat behind the data. A senior scientist who spent 30 years working on the laser systems describes the early days with a wry smile. Back then, he says, the entire concept was considered a long shot, a beautiful theory in search of an impossible technology. His motivation was not a single eureka moment, but a stubborn belief in a fundamental truth about the universe, a conviction that if Einstein was right, the effort was worth it, even if it took a lifetime. He speaks of the camaraderie forged in the face of endless technical challenges, the shared purpose that turned a global team into a kind of family. These are the narratives that transform science from a cold collection of facts into a living, breathing quest. When we hear a researcher describe the emotional roller coaster of a false alarm, or the quiet satisfaction of solving a tiny but critical problem with a mirror suspension, the monumental achievement of detection becomes relatable. It becomes a story about perseverance, curiosity, and the universal human drive to understand our place in the cosmos. How does this deeply personal, human side of discovery then travel from the control room to the wider world? The journey is shaped by the powerful lens of the media. A film like Interstellar takes the mind-bending physics of gravitational waves and black holes and weaves them into a human story, making the abstract feel visceral and immediate. While the movie consulted with physicist Kip Thorne to ensure scientific accuracy in its portrayal of a spinning black hole, it also took creative leaps, imagining astronauts surfing the waves of time itself. These depictions are powerful because they ignite a sense of wonder that a dry scientific paper might not, but they also walk a delicate line. For every person inspired to learn more about real science, another might walk away believing a simplified or dramatized version of events. This is the dual role of popular culture. It serves as a gateway, pulling the cosmos down to a human scale, yet it requires us to be active participants in separating the scientific seed from the fictional flourish. Science journalists act as crucial interpreters in this space. When a new gravitational wave detection is announced, reporters translate the complex data into compelling narratives for the evening news or a digital article. They are the bridge between the collaboration's technical paper and the public's understanding, tasked with explaining why a tiny wobble in a laser beam 1 billion light-years away matters to our daily lives. Their accurate reporting is vital. It turns a cosmic chirp into a story about the origin of gold, the fate of black holes, or the expansion of the universe itself, fostering a society that is informed and engaged with fundamental discovery. Social media accelerates this conversation to light speed. A single tweet from a major observatory can alert millions to a new detection within seconds, sparking a global conversation. Hashtags trend, memes are created, and experts can engage directly with public questions, demystifying the process in real time. This instant access creates a vibrant, participatory culture around science, but it also carries the risk of rapid misinformation. A misunderstood headline can spread a misconception just as quickly as the correct information, highlighting our collective need for critical media literacy. The most successful science communication finds a way to balance rigorous accuracy with genuine engagement. It does not dumb down the concepts, but instead finds the human story within the data, the awe within the equations. How do we make the warping of four-dimensional spacetime relatable to someone without a physics degree? This challenge brings us to the essential tools of analogy and metaphor, the translators between the cosmic and the commonplace. A simple ripple on a pond gives form to a spacetime wave. These analogies are not mere decoration. They are the cognitive bridges that allow us to cross from the familiar to the profound. When a teacher describes the fabric of the cosmos as a trampoline, with stars creating depressions and gravitational waves as ripples racing across its surface, a complex four-dimensional concept suddenly becomes something a student can feel and visualize. This translation is vital, for it transforms intimidating mathematics into a shared story, making the architecture of the universe accessible to anyone willing to listen. The power of a well-chosen metaphor lies in its ability to make an abstract idea not just understandable but memorable. You are more likely to recall the cosmic symphony than a lecture on metric perturbations, and that initial spark of recognition is often what fuels a deeper curiosity to learn more. Yet every analogy has its breaking point. The trampoline is a two-dimensional sheet, while spacetime is a dynamic, four-dimensional continuum. The pond ripple moves through water, a medium, while a gravitational wave is a distortion of the medium itself. A careful communicator knows when to use the metaphor to open a door, and when to gently set it aside to explore the richer, more nuanced reality behind it. This is why educators and scientists are in a constant, creative dialogue to refine these tools. As new discoveries pour in from observatories, the metaphors must evolve to keep pace. How do you explain the polarization of a gravitational wave or the concept of a standard siren without leaning on the crutch of jargon? The answer often lies in finding a new, more precise comparison, perhaps comparing the wave's polarization to the way you twist a towel, or a standard siren to a car horn whose blare directly tells you how far away the car is. This creative process does more than just explain. It actively enriches the relationship between science and the public, turning complex research into a collaborative conversation. In a classroom, these strategies come alive through interactive models. Students might use slinkies to physically model compression waves, or use two marbles on a stretched spandex sheet to simulate orbiting black holes. These hands-on experiences cement the analogy in a tangible way, engaging multiple senses to build a robust understanding. The goal is never to suggest the universe is literally a spandex sheet, but to provide a conceptual scaffold. Once that framework is in place, the real, strange, and wonderful physics of curved spacetime can be built upon it, piece by beautiful piece. A classroom becomes a miniature observatory when students construct their own basic interferometers using laser pointers and small mirrors. This hands-on activity transforms an abstract cosmic concept into a tangible physical principle they can see and adjust with their own hands. As they gently tap a table and watch the laser spot dance, they experience a direct, scaled-down echo of the challenge faced by LIGO, sensing a vibration against a sea of background noise. These physical models are powerfully complemented by digital tools. Interactive simulations allow students to choreograph their own black hole mergers, adjusting masses and spins to see how the resulting gravitational waveform changes on a screen in real time. Virtual labs grant them access to process data from actual detections, letting them sift through the noise to find the hidden chirp of a cosmic collision, just as professional scientists do. This blend of tactile and digital learning makes the science deeply engaging and personally meaningful. Educational standards are rapidly evolving to embrace these modern discoveries. Curriculum frameworks now increasingly include modules on gravitational waves and multi-messenger astronomy, recognizing that this is not a fringe topic but a central pillar of 21st century physics. This shift prepares students for a world where an understanding of spacetime and artificial intelligence-driven data analysis is becoming crucial across many fields. The teacher's role in this new landscape is more vital than ever. They are not just imparting facts but guiding a process of inquiry, helping students connect the wobble of a laser pointer to the ringing of a black hole a billion light-years away. They foster the critical thinking and curiosity that will drive the next great discovery. This foundational work ensures a pipeline of future engineers, data scientists, and theoreticians who are equipped to design even more sensitive detectors and interpret the universe's whispers. The ripples from these cosmic events naturally connect to other scientific disciplines. The laser physics at the heart of detection is a direct application of quantum mechanics. The cataclysmic collisions that create gravitational waves are also the furnaces of nuclear astrophysics, forging the heavy elements that make up our world. The data analysis techniques developed to find these faint signals are now used in medicine and finance. Seeing these interdisciplinary links helps students appreciate that science is not a collection of isolated subjects, but a single, integrated effort to understand the world and our place within it. The search for a cosmic whisper demands a fusion of minds from seemingly unrelated fields. An astrophysicist might understand the mathematics of a black hole collision, but it is a computer scientist who writes the machine learning algorithm that can find that specific pattern buried in years of terrestrial noise. These algorithms, trained on millions of simulated signals, act like sophisticated filters, sifting through the constant hum of the planet to identify the faint, telltale chirp of a distant merger. This is not a minor collaboration, it is the very backbone of discovery. Without these advanced computational techniques, the data stream from the detectors would be an indecipherable roar. The same signal processing methods that once helped clean up crackly telephone lines are now being refined to isolate a spacetime ripple from a billion light-years away. This cross-pollination of ideas accelerates progress in both directions, as the extreme demands of gravitational wave science push computer science to develop faster, more intelligent data analysis tools, which then flow back into other fields like medical imaging or financial modeling. The interdisciplinary web extends deep into engineering, where teams design suspension systems that isolate the mirrors from vibrations with a precision that redefines the possible. Materials scientists develop new coatings for those mirrors to minimize the tiny amount of heat they absorb, which could itself create a distorting signal. Even the cosmologists play a crucial role, for their models of the early universe provide the theoretical framework that tells the data analysts what kind of ancient signals they should even be listening for. This unity of knowledge, where a breakthrough in laser stability or a new statistical method can directly translate into a deeper understanding of the cosmos, demonstrates that the most profound questions cannot be answered within the silo of a single discipline. It is in the fertile ground between these fields where an expert in one area looks at a problem from a completely fresh perspective that true innovation ignites. This environment is a perfect incubator for the unexpected, where a search for one thing can lead to the accidental discovery of something entirely different. A faint, unexpected blip in the data can be more valuable than 1,000 confirmed signals. The history of science is filled with these fortunate accidents, moments where a scientist looking for one thing stumbles upon something entirely different, reshaping our entire understanding of the cosmos. The discovery of cosmic microwave background radiation, the afterglow of the Big Bang itself, came from two radio astronomers trying to eliminate persistent static from their antenna. They initially thought the signal was caused by pigeon droppings, but their open-minded investigation revealed the echo of creation. Gravitational wave astronomy is perfectly poised for its own serendipitous revolution. Our detectors are listening to a dark universe we have never perceived before, so the potential for a complete surprise is immense. What if we detect a signal that pulses with a rhythm no binary system can explain? It could be the vibration of a cosmic string, a hypothetical defect in spacetime left over from the early universe, a crack in reality itself snapping like a whip. Or perhaps we will find a merger between objects of impossible mass, something that should not exist according to our current models of stellar evolution. Such an anomaly would force us to rewrite the rules, to ask new questions about how matter behaves under the most extreme pressures. How do you prepare for a discovery you cannot even imagine? The answer lies not in building a specific detector, but in fostering a certain mindset. It requires creating a scientific culture that prizes curiosity over conformity, where a young researcher is encouraged to chase down a strange day, a glitch, instead of dismissing it as noise. The complex algorithms that sift through the data are now being designed to flag unusual patterns that do not match any known template, actively searching for the outliers and the oddities. This intellectual flexibility is our greatest asset. It allows us to pivot when the universe throws us a curveball, to see a failed experiment not as a setback, but as a clue pointing in a new direction. The most profound discovery in this new field might not be the one we are meticulously hunting for, but the one that quietly finds us when we are listening for something else entirely. This readiness for the unexpected is what will ultimately allow our theories to evolve, bending and adapting to the true, strange shape of reality. A scientific theory is not a rigid cage, but a living scaffold built to hold the weight of new evidence. Gravitational wave observations are the ultimate stress test for this structure, constantly probing the foundations of our models. Every time a ripple from a distant collision arrives, it carries a precise prediction from Einstein's general relativity. So far, the theory has held firm, its mathematical elegance matching the universe's own. But what happens when the data tells a different story? A single, clear anomaly, a subtle mismatch in the waveform, or an unexpected polarization would not break the theory. It would illuminate it. Such a moment forces a beautiful crisis, a collective reevaluation that pushes scientists to ask better questions. It demands both humility, to accept that our current picture is incomplete, and immense creativity, to imagine what new physics could explain the discrepancy. This is not a failure of science, but its deepest strength. The entire process is iterative, a loop of prediction, observation, and refinement. Think of it like tuning a musical instrument by listening to its sound. Each new detection is a note that helps us adjust the strings of our understanding, bringing our model into closer harmony with reality. This willingness to be proven wrong, to let the universe itself be the final arbiter of truth, is what separates a living scientific endeavor from a stagnant dogma. It is how we move from simply describing what we see to genuinely comprehending why it must be so. This dynamic process of adaptation applies far beyond the cosmos. In medicine, a new symptom forces a doctor to reconsider a diagnosis. In technology, a software bug reveals a flaw in the underlying code. The same principle of testing, learning, and refining guides every field that seeks real, verifiable knowledge. Our journey through the hidden architecture of the universe, from the first chirp of colliding black holes to the faint hum of creation, demonstrates a profound truth. We are not merely building a static map of the cosmos, but learning how to navigate an ever-deepening reality, guided by the quiet ripples in spacetime. Our journey through the whispers of spacetime reveals a cosmos far grander than we ever pictured. We have traced the path of a ripple from the final embrace of two black holes, felt the tremor of neutron stars forging gold, and listened for the faint echo of the universe's own birth. Each signal is a key, unlocking a deeper layer of the cosmic architecture, from the dark matter scaffolding to the dark energy accelerating its expansion. Yet for all we have learned, this new sense of hearing is still in its infancy. The detectors of tomorrow will listen with a clarity we can scarcely imagine, turning today's faint murmurs into a resounding chorus. They will hear the first stars live and die, trace the growth of galaxies from the dawn of time, and perhaps even capture the primal vibrations from the instant of creation. Let this knowledge change the way you see the night sky. That vast, silent expanse is not silent at all. It is a dynamic, vibrating arena, humming with the music of colossal events. This ongoing quest to understand our place in this grand design relies on a shared sense of wonder and the collective support for the curious minds who dare to listen. Your engagement fuels this exploration. Share your awe and your questions in the comments below, and join us as we continue to follow these cosmic ripples, unraveling the universe's greatest secrets.